Hello everyone. In today's session, we are going to explore one of the foundational concepts in artificial intelligence, that is production systems. So, this helps you to understand more about knowledge representation and such. So, this topic is absolutely central to how machines reason and make decisions. So, by the end of this session, you will understand what a production system is, how its core components work together, and the different types of production system that exist, and how they are used to solve the real world problem. So, to begin, first we will see the definition of the production system. A production system provides structures that facilitate describing and performing the search process. So, what it really means. So, think of a production system as a structural framework. So, this helps us to describe what we know about the problem and how we can move from a current state towards a solution. So, this production system will help us to organize the problem. Okay, so there are four components generally. These are the essential component. The first component is the set of rules. So they are also called as productions. So generally each rule has two parts. A left side, which is a pattern or a condition, and the right hand side, which is an action. It's like a if then condition rule. Okay, so if the condition is satisfied, then take the particular action. So these rules are the heart of the system. So they encode the knowledge and logic we want to use. Okay. The second component is one or more knowledge databases. So this is where the information about the problem is stored. The database might hold both permanent background knowledge, things that are always true, and temporary problem specific data that changes as AI works through a particular task. Next, the third one is the control strategy. This determines the order in which the rules are examined and applied. Okay, so it also handles conflicts. So what happens when more than one rule could fire at the same time? When more than one rule is satisfied for a particular condition, then what happens? So without a good control strategy, a production system could loop endlessly. So it can even make poor decisions. So a control strategy is very, very important. The fourth and the final component is a rule applier. It's also called as an inference engine. This is the mechanism that actually checks which rule matches the current state of the database and then executes them. So, these four components, rules, databases, control strategy, and the rule applier, forms a complete production system. It's like an engine, fuel, steering wheel, and a driver. Okay, so all these are very, very important. Okay, so this framework will definitely lead to a good solution. Now we will discuss each and everything in detail. First is about the rule. So, as we already said, a rule has two sides, that is the left hand side and the right hand side. The left side is the condition, it specifies the pattern that must be present in the database for the rule to be considered. Okay, it should be only if the left side is available in the database, that will be checked throughout the database, and if that rule matches, okay, on the left side, then we say the rule is triggered. and the corresponding action should happen. So the right side describes the action. So when a corresponding rule fires, the action on the right side is executed. Okay, this action might add new information to the database, it might remove the old information, or it might change some existing state. So in effect, firing a rule moves a system from one state to another state. That's how the progress happens. For example, if you take a chessboard, when you make initially the board is arranged. Okay, so when you make one move, the board is changed. The we have navigated from one position to another position. Okay, right. Suppose we can take one more example. Like suppose we are building a system to diagnose whether a patient has a fever or not. So what you will try and check in the left side. If the patient temperature is more than some 38 degrees, if this rule matches, then condition will be executed. We can conclude that the patient has a fever. Okay, the condition is here the temperature check. Okay, right. The action we are going to take is the diagnosis. What happens when the temperature exceeds the corresponding level? Okay. Next, we will talk about the knowledge base, the knowledge databases. So this stores all relevant information the system needs. Some of the information is static, like general knowledge that doesn't change. Okay, like the fact that normal human temperature is around 37 degrees Celsius. That doesn't change, that's common. So other parts are dynamic. So they represents the current state of the specific problem being solved. Okay. So the actual temperature reading of a specific patient right now, that is the dynamic state that changes. Current status, I mean the static status, every human being will have 37 degree. The dynamic status, every human being when he is having a temperature, it varies with respect to the patient. So the database can be structured in many ways. Okay, as simple list of facts, as attribute value pairs, or even as complex relational structures. So depending on what the problem requires. The point here is the rule acts upon the database. That is, the left side will come and match with the database and it will modify it according to the rule. Okay, so as the problem is processed, it gets modified. Next is about the control strategy. So we have discussed about what are the two things we have discussed? We have talked about rules, we have talked about knowledge base. Now we are going to talk about the control strategy. So control strategy already we discussed, it's very, very important, right? So this tells the order in which the rules are executed or compared to the database. Okay. So this is what makes a production system intelligence and it's not mechanical. So without a control strategy, even if you have a bag of rules, so you might not know which rule to apply, when you have to apply which rule. So the control strategy specifies the order for comparing the rules to the database. First you do this, second you do this. Okay. Generally, you can follow two approaches. One is forward chaining approach or the backward chaining approach. In a forward chaining approach, you start from the known facts, then keep firing the rules until you reach a goal. In a backward chaining approach, you start from the goal and work backwards to see the facts. So both are valid strategies. So, and the choice depends on the nature of the problem. Whether you're going to use forward or backward, that depends on the nature of the problem. The control strategy also helps in resolving the conflicts. Okay, when the conflict will come when multiple rules matches at one particular pattern for one particular pattern. So it will help us to find the most specific rule based on the predefined priority order. Finally, we have to talk about the rule applier. Already we discussed what is a rule applier, right? It's like an inference engine. It implements the control strategy by continuously cycling through the steps. It matches the rules against a database, it resolves the conflicts if multiple rule matches, and then fires a particular selected rule. So this will happen until you find or if you reach the goal state. Okay. Now we will discuss about various types of production system. So we understood the components. Now we'll talk about the different types of production system. The first category is the basic languages. So these are the foundational programming languages designed specifically for building the production systems. The most famous examples are OPS5 and ACT. Okay, so this OPS5 was widely used in early AI researchers and expert system. Now this ACT is a cognitive architecture and it was developed by John Anderson that models human memory and problem solving. The second category is expert system shells. So these are more sophisticated tools. It's complex hybrid systems. It is designed to make it easier and to build a domain specific expert system without starting from the scratch. So they provide the production system infrastructure and domain expert simply adding the rules. So examples include Clips and JESs. The third category is the general problem solving architecture. So the example is SOAR, which stands for State, Operator and Result. So it was developed at University of Michigan. So it was a unified cognitive architecture. So unlike the expert system shells, so it can handle a wide range of tasks from playing games to controlling the robots using a single consistent architecture built on the production system principles. Now we'll talk about problem solving using production systems. Okay. First one. Reduce the production to one with a precise statement. So this means taking a real world challenge, vague real world challenge, and expressing it in a clear, formal way. For example, instead of to find the shortest route, generally to tell a vague statement like find the shortest route, you state given cities A through Z and distances between them, find a sequence of cities from A to Z. So that minimizes the total distance. That's the first step. Second one is define the problem's state space. So include the start state and the goal state. The start space is the complete set of all possible situations the system could be in. Okay. The start state is where you begin. Like if you have A to Z, then A might be your starting position. So what is currently known or true? That is going to be your starting position. The goal state is what you wanted to achieve. Like if you take a chessboard, the coins are arranged in their respective positions with the beginning of the board. The goal state is a checkmate. So if you take a route example, the start is we have to start from city A and the goal state is we have to reach city Z. That is the defining the problem state space. Third one is defining operators from moving through the space. Now we have a big space to move, right? So we have to define the operators. Operators are nothing but what are they? They are the actions. Okay, when your left side rule matches, your corresponding right hand side rule triggers. So this triggering transforms from one state to another state. So in the route example, for example, if you take the same example, an operator might be travel from city X to adjacent city Y. So when you're making a move from city X to city Y, so it will change your current location. The last one is Step 4, that is search for a path from initial state to goal state. This is where the control strategy comes into the play. The system applies the rules, operators iteratively, it will start exploring the state space until it finds the goal state. So there will be a sequence of steps happening from starting to reaching. So to start from a start to reach the goal, multiple search procedures might be there. Breadth first search can be used, depth first can be used, some heuristic models can be used like A star. So depending on what kind of problem we are dealing with, the corresponding search strategy can be used. The fourth step is the universal recipe for each using the production system to solve the problems is very, very important. It might be anything. You can start solving a simple puzzle to any medical diagnosis or to a robotics. So what we understood is, so your production system is based on, it's like a planner for you. It is starting. You have to have the four important things. Okay, to reach from a start state to a goal state. Like first one is you should know the rules. Second one is you should know about the knowledge database. Third is the control strategy. And the fourth is the rule applier. So the references are taken from Stuart Russell, Peter Novick, then Parag Kulkarni, and Elaine Rich and Kevin Knight. Thank you.